not going to see the model by Duranton and Turner, published in the Review of Economic Studies in 2012. The title of the paper is Urban Growth and Transportation. This is a model that provides a mathematical representation of a city, particularly how employment in the city relates to the stock of transport infrastructure in the city. It provides a very nice introduction to this class of models of urban economics. They can be very useful to address all sorts of questions related to regional ecosystems that can be of interest for strategy scholars. And it shows in a simple way what are the key elements of the class of models, but also it provides a very tight connection between the empirical analysis and the theoretical framework. The equilibrium setup that we're going to find, the equilibrium formula we're going to find, can be easily rewritten into regressions that can be run empirically. And the other way to think about that is that, if you have data, in this particular case, on employment and on stock of transport infrastructure, and you run regression to try to understand the correlation between these two, the model can help you interpret this correlation, linking it to a number of other things, like agglomeration economies, for example. So it's, in my view, a very nice way to use a theoretical framework to guide and interpret empirical work. Okay, we're going to see a simplified version of the model by Duranton and Turner, published in the Review of Economic Studies in 2012. The paper is titled Urban Growth and Transportation. There is a representative consumer that has a utility that is equal to A times C with exponent 1 minus alpha times X with exponent alpha divided by alpha with exponent alpha and 1 minus alpha with exponent 1 minus alpha. So this is exactly the utility in the paper under the parametrization that beta is equal to 0. So in the paper they have an extra term here, L, with exponent beta. If we set beta equal to 0, that L disappears, and the utility is exactly the same as the one that I give here. So this is a simplified version. You should think about consumers living in these cities doing only two things. Either they drive around the city, or they consume, and consuming, living in the city, they also enjoy some amenities in the cities. And this is captured by this utility function. The term A is a proxy for the amenities of living and in the particular city. The term X is the amount of driving that the consumer does. And the term C is the consumption of all the other goods. So essentially is a numeraire composite good. Think about all the other possible consumption that you can have, like housing, food, and so on. This is normalized such that the price of 1 unit of C is equal to $1. Okay, cost $1 to consume a unit of C. In terms of driving, we set the price of driving equal to P. The consumer has a wage of income equal to W, and therefore the budget constraint for the consumer that lives in this city is equal to C plus PX. Okay, what I spend in consumption plus what I spend in driving has to be equal to my income. Now, as you can see, this is just a simple problem, really. Econ 101, Microeconomics 101. You have a utility function with two goods, C and X. You have an income, and you have the price of the two goods, P and 1. So the first thing that we're going to do is really to solve for this problem and find the optimal consumption and the optimal value of X. Okay, so we have to find the optimal C and X. This is again a trivial standard introductory problem in economics. This is a function that looks very similar to a Cobb-Douglas. Actually, it is a Cobb-Douglas, but with these extra terms here that are not typically in introductory textbooks. Just in case, for those of you that are really not seeing much of consumer theory, I'm going to solve for the optimal, but for those of you that see right away how to get to the optimal consumption, you can skip a couple of minutes in the videos. But let me just, to be complete in the analysis, really to solve for the optimal U and for the optimal value of C and X. Okay, let's go through the consumer utility problem. This is the utility function. This is the income of the consumer. So if you remember the basic process that you do in economics to find the optimal consumption for the consumer is to set the marginal rate of substitution is equal to the derivative of the utility with respect to C divided by the utility of the derivative with respect to X is to be equal to the price ratio. And the price ratio, remember, the price of good X is 1, or good C is 1, the price of good X is P. So this is one condition that needs to be satisfied at the optimal. So what is the utility of the derivative of the utility with respect to C? This is equal to 1 minus alpha times A, C with exponent negative alpha, X with exponent alpha, divided by alpha with exponent alpha, 1 minus alpha, the multiply is 1 minus, with exponent 1 minus alpha. The derivative of the utility with respect to X is equal to alpha times A, C with exponent 1 minus alpha, times X with exponent negative 1 minus alpha, divided by alpha with exponent alpha and 1 minus alpha with exponent 1 minus alpha. Now the marginal rate of substitution is equal in this case, if I take the ratio of these two things, to 1 minus alpha X divided by alpha C. So try to take the ratio of these two. You can see a lot of things simplifies. But 1 minus alpha stays here, X times alpha becomes multiplied by X 1 minus alpha and becomes X, and below alpha here stays, and C 1 minus alpha becomes multiplied by C times alpha, so it becomes C. So the marginal rate of substitution, it's equal to 1 over P if this condition is satisfied. That gives me that C is equal to Px times 1 minus alpha divided by alpha. Now I'm going to use the second important condition, that is the budget constraint. I know from the budget constraint that W is equal to C plus Px. So I can write this as Px times 1 minus alpha divided by alpha plus Px equal to W. Or this can be written as W equal to Px that multiplies 1 minus alpha divided by alpha plus alpha, okay? And this is essentially equal to px divided by alpha. So the condition here gives me that the optimal x star as function of the price and the wage is equal to alpha w divided by p. Now if I want to find the optimal c star, the optimal c star is equal to p x star 1 minus alpha divided by alpha, and replacing x star with this formula gives me 1 minus alpha times w. Okay? And this is the result. The optimal consumption of x is alpha w divided by p. The optimal consumption of c is 1 minus alpha times w. And is a standard property of the utility function that are Cobb-Douglas. So this utility function that have exponents like this. The exponent of c essentially tells me the fraction of the income that is gonna go in good C. And the exponent of alpha also tells me the fraction of income that is gonna go in good X, divided by the price of the good I obtain the actual consumption of these goods in the optimal. Okay, this is the utility function in the model, and we solve it obtaining the optimal x, right? We call it x star, and the optimal c that we call c star. Optimal in the sense that it maximizes the utility of the consumer given the income of the consumer and given the price of the product. So these x's and c were solved to be function of p and w, right? Now the model then moves to work with a different type of utility function. This is what is called the indirect utility function. Okay, indirect. The utility that is written as function of the income and the price. And is obtained by replacing in the utility function the optimal consumption of level C star as function of P and W, and the optimal consumption of X as function of P and W. So if I replace in this formula here the value of C and X that I obtained before, and if you remember the optimal value of X was equal to alpha W divided by P, the optimal value of C was equal to 1 minus alpha W. So replacing this in the utility function, I obtain what is called the indirect utility function. As you will see, this indirect utility function is going to be a very tractable and simple formula. And the fact that we're working on the indirect utility function explains why the main utility, the direct basic utility here, has all these alphas down here those are non-standard alphas, but are really useful to simplify a lot when I move to the indirect utility. So what is the indirect utility in this particular setup? Well, let's replace C and X with these two formula. So V of WP is equal to A, that multiplies 1 minus alpha times W with exponent 1 minus alpha. That multiplies alpha W divided by P with exponent alpha, divided by alpha with exponent alpha, and 1 minus alpha with exponent 1 minus alpha. This can be written as A times 1 minus alpha with exponent 1 minus alpha times W with exponent 1 minus alpha times alpha with exponent alpha times W with exponent alpha, divided by alpha with exponent alpha, 1 minus alpha with exponent 1 minus alpha divided by p with exponent alpha. As you can see here, a lot of things can be simplified, especially these alphas and 1 minus alphas, right? And eventually this can be rewritten as a times w divided by p with exponent alpha. So this is the indirect utility, and as you can see, it becomes a much simpler to play with, and it gives me essentially the utility to the consumer if he lives in the city, when the amenity level is A, the income is W, and the price of driving is P. Okay? So we went from something like this to a much more compact and easy to handle formula. So we have seen this problem of the consumer. Now the model eventually is gonna indicate that there are n consumers that are going to come and live in the city. And how is that this n is determined? Well, it's determined by a number of other assumptions that are made in the model. First, it's going to depend on the wage that these people get in the city, and the wage is assumed to evolve according to the following formula. W is equal to W lower bar times n with exponent lambda, where lambda is a positive number. So this is a function that tells you essentially that the more people are in the city, the greater is the wage that you're getting in the city. Because lambda here is a positive number, and it gets an increasing function. This idea that the wage increases with the number of people in the city, it's called essentially the assumption of agglomeration economies. And in the paper is a discussion on the empirical evidence about this, and some kind of support for this assumption. The second thing that determines how many people are living in the city is how expensive it is to drive around, how costly it is to drive around the city. And the cost of driving here is assumed to depend on the following formula, is equal to nx divided by r with exponent delta. Now, the idea here is that as the number of people in the city increases, and as the number of amount of driving by these people increases, the cost of driving goes up. So here also in this case delta is greater than 0. But the cost of driving decreases the more roads are in the city. Okay. So this delta, essentially, what this delta captures is the elasticity of the transportation cost to the amount of road provided, essentially. And the final assumption that is made is that if people don't live in the city, they live in the countryside, and in the countryside they make utility, they get a utility equal to U lower bar. So whether or not to come and live in the city is pins down to a comparison between the utility that I get in the city, that we said is equal to V of PW, and the utility that I get in the countryside. If this utility is greater than the utility of the city, I'm not staying in the city. So people in the city are going to leave. So this N is going to go down. The amount of people living in the city is going to go down. If the utility in the countryside is smaller than the utility in the city, then you should expect more people to leave the countryside and come to the city. So this N here is going to go up. And the process is going to stop, and you're going to reach an equilibrium at the value of N in which the utility of being in the countryside is exactly the same as the utility of being in the city. So there is some kind of equalization between the utility of living in the city and living outside the city. So together, these three formulas in particular, plus the formula of the indirect utility function that we derived before, allows us to really solve for the equilibrium and use the equilibrium to understand the relationship between various parameters. More importantly, what is central in the paper that is going to be derived in the next part of the video is what is the relationship between the total amount of people living in the city and the road provided. So if I increase or decrease the stock of roads in the city, should we expect more or less people coming in the city, and how much this effect depends on the other parameters of the model. Okay, we're not going to solve this model. There is quite a bit of algebra involved, but I'm going to go through all the steps to show you how you reach to the equilibrium of this model, the characterization of the equilibrium. The first step, we're going to try to get a function of p that depends on the number of people that live in the city and the stock of roads in the city. The idea is to start with the function that we saw before that tells me that the cost of driving is equal to the ratio between nx and r with exponent delta. This can be rewritten using the function of x that is equal to the optimal x in equilibrium that we got from the maximization of the consumer problem. So the optimal x was alpha w divided by p. So this is how this function can be rewritten using that result. And this can be also written, consider the fact that w, it's evolving according to w lower bar times n with exponent sigma divided by r p. Okay, so this is the function of p as function of n and r essentially, and all the other are exogenous parameters in the model. To better solve for p here, I can rewrite this as p with exponent 1 plus delta is equal to alpha w lower bar n with exponent 1 plus sigma divided by r with exponent delta, or p equal to alpha w lower bar n with exponent 1 plus sigma divided by r with exponent delta divided by 1 plus delta. Okay, so this is the first formula that I wanted to get. Now we're going to combine this formula with the formula that tells me that in equilibrium the utility of the individual living in the countryside is to be equal to the utility individual living in the city, that we found the indirect utility was equal to a w divided by p with exponent alpha. Okay, combining these two formulas, we're going to get the relationship between the total amount of people living in the city and the stock of roads of the city. Okay, we said that the utility of people living in the countryside to be equal to the utility of those living in the city, aw divided by p with exponent alpha. So now we can use the formula that we got for w and p here to build on this relationship. This can be written as u lower bar is equal to a times w lower bar times n with exponent sigma. So this is the function that tells me that the wage depends on total amount of people living in the city, divided by p. If you remember, we just derived p as function of n and r2. This was equal to alpha w lower bar n with exponent 1 plus sigma divided by r times alpha delta divided by 1 plus delta. This is the kind of key formula here, and what we're going to do is to try to solve essentially this one by solve for n and having a more tractable formula that makes n as function of r. So I can rewrite these things as u lower bar is equal to r, the exponent alpha delta divided by 1 plus delta times n, the exponent sigma minus alpha delta times 1 plus sigma divided by 1 plus delta. That multiplies a term that is equal to a w lower bar divided by alpha w lower bar with exponent alpha sigma alpha delta divided by 1 plus delta. So this r here is just moving this on the top. This n here is just the difference between this exponent and the exponent of this part here. And this is the remaining, is all the terms that remain that are not related to r and n. We're actually going to call this term here z for simplicity. Okay, we're going to call it z for simplicity. So we can rewrite this as u lower bar divided by z is equal to r with the exponent alpha delta divided by 1 plus delta times n, and this can be written as sigma that multiplies 1 plus delta minus alpha delta multiplies 1 plus sigma divided everything by 1 plus delta. So here I have on both sides 1 plus delta in the exponent, and I can move it on the other side. So this can be written as u lower bar divided by z with the exponent 1 plus delta is equal to r with the exponent alpha delta times n with the exponent sigma 1 plus delta minus alpha delta 1 plus sigma. And finally I can solve for n. This gives me that n is equal to u lower bar divided by z with the exponent 1 plus delta divided by sigma times 1 plus delta minus alpha delta 1 plus sigma times r times alpha delta divided by alpha delta 1 plus sigma minus delta 1 plus delta. Okay, this is the function that I wanted to get. Is a function that in which I have n as function of r with an exponent and other parameters that are not related to r. And it tells me essentially that an increase in r is going to generate variation in n according to this formula here, and the elasticity may depend on the exponent here. Actually, for practical work, this formula is extremely useful because the exponential relationship between the variable can quickly translate the formula into a regression to run. So if I take a log here on both sides, I have the log of n, okay, log of the total amount of people living in the city, is equal to the log of this value here that I'm gonna call a, plus the log of the stock of roads with an coefficient here b, where b is exactly equal to this exponent. Okay, b is equal to alpha delta divided by alpha delta times 1 plus sigma minus sigma multiplies 1 plus delta. So I want to conclude the analysis of the model by discussing a bit what we have derived. We have derived a function of n as function of r in a logarithmic form that give me also an interpretation of the coefficient here on log r that is related to the parameters of the model. So first of all, let's try to understand what is this b here. This b is when you have log is an elasticity. Is how much employment should change if you change of 1% the provision of roads in the city. So that's an elasticity. And the fact that it is linked to the parameter of the model can be used in a variety of ways in more applied work. For example, I can use estimates that come from other sources for these parameters to calibrate, getting essentially a value of this elasticity. So for example, alpha is the share of transport expenditure of a average consumer in the United States, and Duranton and Turner discussed that these estimates that have been done is that this is about 13%. This delta here is the elasticity of transportation cost to road provision. So this is work that they have done, Duranton and Turner, in previous publications, estimated this elasticity to be equal to 0.06. The sigma here is the estimate of agglomeration economists. There are a lot of estimates in the literature. Rosenthal and Strange have a survey of the literature that suggests that the value of this is between 0.04 and 0.08. So by using these estimates, someone can back out essentially B. So even if I don't have any data on N and R, but I just have this formula and some numbers from previous literature, I can come up with an estimate for the elasticity of employment respect to road provision. More importantly, someone can have data, can have data on total amount of people living in a city and roads, and estimate this parameter beta from the data, from a regression. Then what the model tells you is that this elasticity can actually be thought as a combination of other forces. So if I have some information on the other forces, for example, I have an estimate of alpha, I have an estimate of delta, using the elasticity that I estimated in my work, I can come up with an estimate of sigma, for example, that is the agglomeration economies. Okay, so from estimating how much employment changes with road provision, I can come up with an estimate of agglomeration economy. Okay, so this is, I think, a very useful modeling tool. In general, we have seen a particular example of linking growth of a city and employment in a city with a particular variable that is road provision. But someone can write a similar model using a different variable instead of R, using some other characteristic of the regional ecosystem that you may think is important to determine total employment and growth. And models like this allow you to really interpret much more precisely the estimates that you get from your empirical analysis. Okay, you can think about this: an estimate that links employment with the variable of interest, not just at the elasticity of these two things, but also as a way to get insights into additional economic forces that are driving this elasticity.